Hi, my name is Amit Erraguntla,
My name is Nikhil Pesaladinne.
And my name's Arnav Jain.
and today we'll be presenting on our application of quantum Fourier transforms to decompose and restructure low-cost chemoresistive gas sensor data. So we'll be going through our entire research process and how we came up with this project idea. So currently, air quality pollution concentration sensors are very expensive and cost around $20,000. And even though they're so expensive, they're only able to measure a single compound. So for example, rather than giving an overall measure of air quality, they collect information about a single pollutant like carbon dioxide or nitrogen oxide. And while there are cheaper sensors, the issues with them are that they're inaccurate or they output electrical resistance values rather than a parts per million concentration. So what these cheaper sensors do is in on them there are certain chemicals that react with pollutants in the air, and these reactions cause electrons to be emitted, and then the sensors pick up the resistance values to the current generated by the sensor rather than creating an actual ppm concentration of the pollutant in the air. So our goal was to find a way to map these electrical current resistances into a parts per million concentration. And that way we would be able to use the cheaper sensors to do the same thing that the current expensive sensors do. And in addition, with this project, we plan to study the cyclical nature of air quality data. For example, early morning spikes in air quality due to traffic and commuting to work, and also variations between seasonal differences such as winter and summer. So our research question was, could we employ a quantum Fourier transform or QFT to decompose an electrical resistance into individual concentration values of various pollutants? And is this process better for the cyclical nature of air quality data? So going into our methods, um, so like I said before, are the cheaper sensors measure the chemoresistivity of the air through various compounds. So these compounds such as zinc oxide or tungsten oxide are on the cheaper sensors and they react with the pollutants in the air. And then this reaction causes electrons to go through the sensor, and then we pick up the current and the resistance for that current generated by that reaction. So as you can see below, we have a time series data with each sample taken at hourly intervals, and then we have the electrical resistance to a specific compound. And then these compounds are also correlated with certain pollutants such as NO2, ozone, or CO.
And so now for features of our finalized data set. So as Amit mentioned before, we have the 8 sensors, which represent the chemoresistive materials that interact with the air. And for each of those sensors, we have 4 other factors, which are the actual electrical resistance, the heater resistance, the heater voltage, and the age of the sensor. And in addition to this, we also included external variables we don't employ any quantum processes on those, but those will come into play later when we try and recombine our data into a final ppm value. And so these external values are time variables like the hour and the day of the week, environmental variables like the temperature outside and the pressure, and weather variables like the wind direction and the wind speed. And so before we get into the quantum analog, I first want to talk about just the classical Fourier transform. And what the classical Fourier transform does is it decomposes one complex wave, as you can see here in the bottom right, into individual sinusoidal waves. And the benefit of this is that it takes a complex function and breaks it down into much simpler individual functions that we can then study. And this is classically implemented through the fast Fourier transform, this formula you can see here. And now for the quantum analog, which is the quantum Fourier transform. And before we employ any quantum strategies, we first have to encode all of our classical data in a quantum fashion. And we do that through the usage of quantum bits, or qubits. And as you all know, like in a classical sense, bits are represented as 0 or 1. But in the quantum world, instead of 0 or 1, the quantum bits are represented as spins or vectors, which range anywhere from 0 and 1. So you can see how they naturally encase a lot more information in the same amount of space. And another thing is that since these vectors are like spinning as they rotate from 0 to 1, they're naturally cyclical, which made us think that it would be a natural application for this problem. And to see how a quantum Fourier transform works, you can see this graphic at the bottom, which essentially shows that the quantum Fourier transform decomposes the data down into these individual qubits. And all these qubits are rotating at different frequencies, and the differing combinations of frequencies results you can be mapped to individual values, and that's how you decompose an overall set of data down to individual qubits.
Okay, so now that we know how quantum Fourier transform and Fourier transform work, we want to now apply it to our data and our problem of converting concentrations or converting resistances to concentrations. So how we do this is through this four-step process. We first take this raw sensor data, we encode it into qubits, we then decompose it with a QFT, and then after we decompose it, we try to recombine the decomposed waves into a ppm value. So in order to implement our code, we first had to pre-process the data with pandas and NumPy. As Amit showed in the graph earlier, the data ranged from 10 to the 8th to 10 to the 9th. So we first had to normalize the data to integers 1 to 64 to make it easier to handle. Then we had to implement the algorithms in SciPy and Qiskit. We use SciPy for fast Fourier transforms and Qiskit for the quantum Fourier transforms. In the image to the right, we can see how we initialized our quantum circuit using Qiskit and ran our model. So in order to run our quantum circuit, we used IBM Q, specifically their IBM Jakarta computer, which had 7 qubits. And in order to train and test our model, we first fit the transform on the first 60 time steps and tested how good it fit on the next 60. So as you can see in the results, especially focusing on the image to the right, we see the green line represents the raw data, the orange line is the quantum Fourier transform, and the blue line is the fast Fourier transform. So as you can see, the orange line fit the data and the curves a lot better than the blue line did, which means it was able to capture the cycles better. In order to quantify this or how successful it was at fitting the data, we used a mean squared error. And a lower mean squared error means it performed better or fit the data better. So for all 3 materials we tested on, the quantum Fourier transform had a lower mean squared error than the fast Fourier transform, which means it performed better. So after we decomposed the data into using the quantum Fourier transform into individual waves, we had to use this data and recombine it into ppm values. So we recombined it using a convolutional neural network. So the inputs were the QFT return values along with other values like the temperature, humidity, and other stuff collected by the air quality sensors. And then we use those as the inputs and we wanted to map those into ppm concentrations. So using a convolutional neural network, we trained it using the inputs and used the ground truth ppm values as the outputs. And after we trained it, we obtained a percent error, which were 3.25% for NO2, 7.28% for O3, and 2.31% for CO, which are pretty low and are comparable to state-of-the-art sensors, which have around a 2% error. So as you can see, with a lot cheaper sensor, we're able to achieve similar error results. So some obstacles we faced during the process of our project was implementing the algorithm. Specifically, we didn't have many qubits. We only had 7 available to us on IBM Q, which means we couldn't train on as much data as we would like to. So if we had 16 or 32 qubits, we could train on a lot more data, which means we could have better cycles, better decomposition, and learn like more important features. Another thing we had is that our data is only 1 year long, which means we couldn't analyze patterns year over year. So if we get data from multiple years, we could identify more yearly trends and cycles.
So overall, we were able to process the raw electrical resistance values from the chemoresistive gas sensors, and then we encoded the data into qubits and decomposed it using a QFT, and then we reconstructed that using our CNN into the concentration of various pollutants. And then ultimately, we only needed one of the cheap sensors data to produce concentrations of multiple pollutants, which saves costs by a lot and also uses less sensors. And we would like to thank Mr. Hanna for his continued support and guidance throughout the project, and also Dr. Gallardo and then the FBK group for providing us with the chemoresistive gas sensor data. And here are our references, and thank you guys for watching our presentation.